Right, I'd like to look a little more at how torque relates to work and also to power. Remember that torque has units of Newton meters. But we've seen problems that have torque acting, that it's a static torque in which no motion has taken place. And so we don't want to just think that because we have a torque acting, that work has been done. And so remember that for work to be done, an object must move. And so if we are to try to understand how to do work with a torque, I think perhaps the best idea is to go back to our basic definition of work as force through a distance. So that's the integral of F dx. Okay. And we can turn, if this is a force that is acting perpendicular to the direction of a radius vector r, then we can turn this force into a torque by just writing the forces r times F. And then that's our torque. And so if we're going to do that, then the dx is equal to r d theta. Okay? And so we could then say that since dx is r d theta here, then all that's left of the dx is the d theta part. So that our work done in terms of a torque must be thought of in terms of some angle through which the torque is acting. Okay? And so the equivalent then to the integral of f dx here is the integral of torque times d theta. All right? And so if we go back up to the data projector, we can see that there are some analogs to our linear and angular motion. We make the substitution that x goes to theta, v goes to omega, and a goes to alpha. Then we go from our linear kinematics equations to our rotational kinematics equations. If we let the mass go to moment of inertia, and we let force go to torque, then F equals ma. If F is replaced by torque, and m is replaced by moment of inertia, and a is replaced by alpha, then notice here that we've got torque equals I alpha is the rotational equivalent to F equals ma. But just with those substitutions, that x goes to theta, v goes to omega, a goes to alpha, m goes to I, and force goes to torque. And so we also see then that the work, which is the integral of f dot dx, if f goes to torque and x goes to theta, then dx goes to d theta, and we have this correspondence then between work done by a linear force through a distance and work done by a torque through an angle. And then with kinetic energy, we have k equals 1/2 mv squared. And so if we let m go to the moment of inertia I, and v go to omega, this becomes our rotational kinetic energy. Now power, we saw before, is force times velocity, but if force is replaced by torque, and v is replaced by omega, we should have an equivalent kind of a relationship for power in a system that has torque. Okay, and so we can say then basically here is that in this example, let's say that the torque is constant. Now, it's not always going to be a constant, but let's set it equal to a constant for this example. If the torque is a constant, then we can pull it outside of the integral, and then the work done is going to be equal to the torque times delta theta. Okay. And then if we want to take the derivative of that, we can say that dw dt is equal to the power. So that's going to be the constant torque times basically d theta dt, or delta theta delta t, in our more specific example here. Just dividing both sides through by the increment of time, that gives us torque times omega is equal to power. Okay, so let's look at an example here where we apply a torque by means of a force that acts on a disk, and we allow the disk to rotate about its center. Then we're applying a torque that's equal to, it's a constant. Let's say that F here is 50 newtons and R is 1 meter. Okay, then the torque would be equal to 50 newtons times 1 meter, or 50 newton meter. Now remember, we don't make the mistake here of calling this a joule just because it has the units of newton meter, because we haven't done work yet. But let's say that this constant force acts perpendicular. So in other words, it keeps acting with the same constant value for the force, 50 newtons, all the way around, and that it acts for a time t equals 5 seconds, like that. Then, what we can do first of all is find the work done. And so this is because of the perpendicular force that acts. And in this case, that torque is a constant value throughout that 5-second interval. Okay, so what we need then is delta theta, because the work done would be equal to torque times delta theta. Okay, so how do we get delta theta? Well, we can go back to our rotational kinematics equations, which look just like our linear kinematics equations. Omega final is equal to omega 0 plus alpha t theta. In this case, that's your change in theta. That's also our delta theta in this problem. 1/2 times omega initial plus omega final times t. Theta is equal to omega naught t plus 1/2 alpha t squared, and omega final squared equals omega initial squared plus 2 alpha theta. Okay, so those are our 4 rotational kinematics equations, which are analogous to the linear kinematics equations. You remember, V final was equal to V0 plus AT. X was equal to 1/2 times V0 plus V final t, x V0 t plus 1/2 AT squared, and V final squared equals V0 squared plus 2AX. So notice here that the V was replaced by omega, the X by theta, and the A by alpha, and if you hadn't noticed that before, that gives us an exact correspondence between our rotational kinematics equations and our linear kinematics equations. But here, we're just interested in finding delta theta. And so what we need to do then is find alpha. How do we get that? Well, torque is also equal to I alpha. Okay? And so alpha then is just equal to the torque divided by I. And so in this case, if this, let's say this disk has a mass of 100 kilograms and a radius of 1 meter, then this is just going to be F times R divided by 1/2 mr squared for the moment of inertia for a disk. We'll assume this is a disk that is rotating about its center. Okay, so that's going to be equal to F, the 1/2 here goes up to the top, over mr. And so alpha then would be 2 times 50 newtons divided by m, which is 100 kilograms, times r, which is 1 meter. And that would give us 1 radian per second squared for alpha. Okay, so we would have in our known column here, let's assume the initial velocity, and it starts from rest. Let's assume that. And we have alpha now as 1 radian per second squared. And we have the time that the torque acts is 5 seconds. Then that means that we should be able to solve for theta by eliminating all of the equations involving omega final, just like we had done before in some of our previous examples. And so that would be this third equation. That one doesn't involve omega final, and so that would give us our value for delta theta. Delta theta would just then be equal to 1/2 alpha t squared, or 1/2 times 1 radian per second squared times 5 seconds squared. Okay, and so that would be 25 divided by 2, or 12.5 radians for delta theta. So the total work that we do in this process then would be the torque, which is 50 newton meters, times how much angle we've swept out, which is 12.5 radians. How much is that? Well, 2 pi radians equals 360 degrees. So 2 pi, 2 times 6 is 12. It's something like 1 complete revolution, because this is 2 pi radians is about the same thing as 1 complete revolution. But we want it in radians here. So that would be times 12.5 radians. And then we can knock that number out. So that would give us 625, and now we can call it a joule. So the work done here is 625 joules. Why can we call it a joule here when we didn't call it a joule there? Well, because the object had to move. So that means that the torque had to act through a certain angle, and in this case, that angle was almost 1 complete turn of the wheel. Okay, so that gives us then our work done. Now what if we want power? Now power is the rate at which work is being done. And so since we have a constant torque acting here, we could say that our average power is equal to the work done, which is 625 joules, divided by how much time elapses, which is 5 seconds. And that should give us a result in watts, or 125 watts. So that is the rate at which work is being done. So in other words, work is being done at a rate of 125 joules per second times 5 seconds gives us a net total of 625 joules of work being done. Now, another way that we could have calculated this would have been to have looked at the power expression from the standpoint of constant torque being applied through a certain rotation rate. Okay? And so for this example then, this is going to be a little different because in this case, to look at power at any given moment, this would be our instantaneous power rather than our average power. So our instantaneous power then can be written as torque times omega. So let's look at a slightly different example here in which we have an object that's rotating, but there are dissipative forces acting. So in other words, there's a force that's being applied, but that force is just enough to keep the wheel turning. So you could imagine this to be like, for example, driving in your car, and your speedometer stays constant. It doesn't go anywhere. It stays, say, at 60 miles an hour. Then that means there are dissipative forces acting, but you're adding just enough force to overcome those dissipative forces in order to maintain a constant velocity. So we could think of the power in that situation as being equal to force times velocity. This is what we showed before as our relationship for power in a linear problem. But in this problem, let's say that we have to apply a 10-pound force, or a 10 Newton force, sorry, through a radius vector here, let's say, of 1 meter, in order to keep omega constant. At 60 revolutions per minute. Okay, so that's the torque required to keep the omega value here at 60 RPM. Let's find the power. Well, in this case, because we're holding omega constant, we can say that our instantaneous power is the same thing as our average power. And so that we can go ahead and just multiply those two together. But 60 RPM needs to be converted into radians per second. And so this we could write then as revolutions per minute times 1 minute for every 60 seconds times 2 pi radian per revolution. So this omega then is the same thing as 1 revolution per second, or 2 pi radians per second for omega. And so we're applying this torque to keep this value of omega constant. And so in that problem, we could say then that power is equal to torque, which is RF times the sine of 90, okay, multiplied by omega, torque times omega. And so that's going to be 1 meter times 10 newtons times omega, which is 2 pi radians per second. So that would give us then 10 times 2 is 20 pi watts. Or that would be the same thing as 62.8 watts. Right, because 2 pi is 6.28, so I didn't really need a calculator for that. I already knew that. So it's 62.8 watts would be the power. Now, how would we use power in that previous example? Why can't I just take the value of omega here that happened when we were applying that torque to that rotating disk? The answer is because the value of omega here is not constant, it's constantly changing. So I could figure out the power at the maximum value for omega, and that would be the maximum power. Or I could figure out the power at the beginning when it's not moving at all, and then that would be 0. Or I could figure out the average power for the average value of omega, which would be equal to our final value of omega over 2. Okay? And so we can use this expression for our first example in which we got that result of 125 watts as being the basically the average power over the entire time interval. But to get that to agree with this, we'd have to figure out omega final and divide that by 2 to get omega average. And then I'll leave it as an exercise for you to show that if you do that, you get the same value for the average power of 125 watts.